Good evening, good morning, and good afternoon, depending where you are. Welcome to the IFAC Workshop Series on Control Systems and Data Science towards Industry 4.0. And this is hosted by the City University of Hong Kong, and along with it, School of Data Science at City University, and also Hong Kong Institute for Data Science. My name is Ji Chen, and I'm privileged to be the moderator of tonight's session, which is creatively called Module 1 of this series. I'd like to begin by welcoming you all from all around the world to join us in this event. I just took a look. There are about 220 colleagues online, and I was told there were over 400 registered. So many of our colleagues may be still on the road. It's a tremendous number. And for that, I'd like to thank the organizers and the IPC members for their tremendous efforts. And I would acknowledge in particular Mark and Sandy for taking care of all the hassles. The COVID clearly did us bad, but inadvertently, it also made it possible for us to gather in this particular manner at this forum from our offices and studies with tea and coffee, which normally is not allowed in a conference room. So you are all from widely different geographic locations and disciplinary backgrounds. So like never before, this by itself is really worth commemorating. The workshop is focused on the themes of control systems and data sciences with an eye toward Industry 4.0. The goal, evidently, is to explore the interplay and the synergy between control, data analytics, AI, and machine learning for, I'd say, including but not limited to industrial applications. We have heard a lot about AI and machine learning in the recent years. There are many successful stories. There have also been doubts and perhaps even more hand wavings and noises. And so this event is most timely thanks to the initiative of Professor Joe Chen, who's also going to be the first speaker. And certainly thanks also to the concerted efforts by many of our colleagues. And I hope, indeed, I believe many of us, especially our students and young colleagues, would benefit from this series. And perhaps some doubts will be erased and noises will be filtered. And more to this point, we control people have always prided control as an enabling technology. But I always have a secret hope that we as a professional community goes beyond that. Instead, beyond responding to technological trends, we actually provide to scientists and engineers in other fields the kind of ideas and brain food, so to speak. So it is also my hope that this series, in particular, tonight's module, will contribute toward that mission. So we kick off the series with tonight's module 1 on aspects of data analytics and machine learning from a controls perspective. As you might have noticed, there will be more to come Yeah, and so please stay tuned for the later modules as well, which are respectively devoted to connections, linkages to chemical engineering and electrical engineering, computer science. So for tonight, we have three distinguished speakers also serving as the panelists. Professor Off Findeisen, Professor Zhou Qin, and Dr. Hong Zhao, with quite a diverse and indeed, in my opinion, it's a perfect combination of academic and industrial backgrounds and perspectives. The way we'd run this session is as follows. Each of the speakers will be allocated 35 minutes for presentation, and we will run that continuously. And after all the presentations are done, we have 35 minutes of a panel discussion, and where we will feature the questions and answers and the discussions. So, and certainly questions from the audience are most welcome, but please type your questions in the chat room, which we will collect and address to the panelists during the panel discussion session. Okay. I would like to express my appreciation to the three speakers for the three wonderful talks, which give us a whole variety of perspectives, utterly different yet mutually complementary. So it's quite educating. So. With that, we move to the panel discussion session. So I take a look at the chat room, and we do have quite a few questions, and I think they are mostly technical questions that are addressed to individual panelists. So before we do that, I guess on behalf of the students and young researchers, I would ask one or two generic, let's say, journal questions instead of technical questions. And hopefully that will give us a broader outlook. At the beginning, we say actually a question for myself. So at my age, I have seen research and for that matter, technological trends come and go. Yeah, and I recall even for AI in the mid and late 1980s, when I was a student, it was quite hot. And I actually took a AI course myself from computer science. I recall the back then the kind of project we do is it's a very popular game called the River Z. But then all of a sudden, sort of disappeared, somewhat like overnight. Now we are seeing a incredible resurgence of AI machine learning. And so is this going to be long lasting? And how is it different this time? And so that's part one of the question. And next, I'm willing to believe this is going to be really, really impactful and for a long time to come. Now, for let's say for a graduate student, a young researcher interested in doing, in making AI and machine learning work for their own respective areas, where to start and what will be the potentially more rewarding topics, niches. Okay, and so this question is addressed to three panelists. And Joe, you want to start?
Okay, yeah, thanks, Jeff, for that general question. I'll be brief. Yeah, I think for Jill and me, we have seen at least two rounds of high peaks of AI or machine learning. The last round was in late 80s until early 90s. Okay, I think this round is happening for about 10 years now, maybe more than that. What's important or unique in this round of machine learning is that it's really driven by applications, by use cases, or actually the industry it has been driving, like Amazon started this recommendation system, Netflix and Google and so on. And also there are a lot of successes in the cognitive related areas for natural language processing, image recognition, and other things that you use. All right, for of course the mobile technology has helped popularize the adoption of this. You use your phone, and many elements in the phone are already based on AI, and that's my view of this round. However, there is this penetration from this cognitive related successes to other areas. For example, financial technology. Okay, and of course this e-commerce based, all the strategies are being changed by AI now. The big challenge for people like in this audience or us is that how do we translate this success of things that's based on big data, data science, and more rich sets of machine learning tools to the industry setting. Okay, we have to make things. We cannot just play with the virtual things. So really, our industry has to be there to make all these things happen. So I think that's our challenge. What I think, I guess my PhD advisor is in the audience. Okay, I did my PhD work on neural networks and statistics. So I think what's really now different in terms of the available tools or understanding of these things is that the machine learning part and statistical part are really merging together. In many leading statistical departments, they study statistical machine learning. And for computer scientists, they are also concerned about all this error control, uncertainty control issues. This is not to say that there are not research that's blindly applying deep neural nets to anything that they think they can apply to. So I don't think that's a healthy thing. However, over time, as you mentioned in your opening remarks, those things will be filtered out. I think there will be actual adoptions over time because we have better understanding of principled application of machine learning and AI tools. Okay, I'll stop there for now.
Yeah. Off, you want to say something?
Oh, sure. Maybe let me add to Joe's remark and also point out, if you say, is it long taking? So nobody can predict the future. That's certainly one of the sentences. But on the other side, I think one of the major things is that at least for some applications, you have a huge technological advancement. And this is also pushed by the companies who first employed these tools, as Joe said. So Amazon, Google, they have been pushing that. And they also have the computational backbone to do that. So they also develop the tools, they support the tool development, and so on and so on. So this is one side. Having said that, however, I would be still, so there's still a long way to go. There was a question in the audience about online learning. So I guess the question needs to be reformulated. Real-time learning for faster applications. Now, one needs to say, what does real-time mean? But this is something where I think this is an area which is upcoming, but I haven't seen that much suggest there. So really, I'm now talking in the range of seconds, milliseconds, which is not that important for chemical processes, one needs to say. So I guess, having said that, for the chemical and the process side, I think these technologies, they will be used and they are already used, because there you have a little bit more time, you can analyze the data you have, and so on. Now, having said all that, so I'm optimistic that it will stay longer. It will not get away because there's also a lot of money invested. But one thing which is also very often overlooked is two things. One of these things is actual data quality. So yes, there is a lot of data, but most often this data is of bad quality. And even though that somebody tells you we have a lot of good data, you look at that and you realize it doesn't contain what you need, or it's too noisy, it has too many outliers and so on. Maybe Hong can comment on that a little bit from the industrial perspective later on. So this is one side, and the other side is what I have seen also collaborating with machine learning people. Do not forget the physics. So I'm at least still a believer, or let's say I have the hope that we will still need in the coming years the 300 years of understanding physics, and don't throw them away by just looking at the data. So saying that there's still a very strong need for especially fusing physical knowledge, physical insights with the data, with the machine learning. And this is something I have seen from the machine learning people. There's a very nice story. So we have a project with on molecular manipulation with the research center in Jülich. And we have been doing that since 5-7 years. And then our colleagues, they said, let's collaborate with machine learning people. Let's use reinforcement learning. And then they started doing that. It looked very good. And after 2 years, they returned and they said, well, they now achieved what we achieved, let's say also in short time, with using physical models. So, and they were very disappointed about that because the people from the computer science, and this is not, I'm not, let's say, fighting against them, I'm only bringing that up, they forgot about the physics. So it's, I think both sides need to actually watch out. We should not forget about the machine learning side, but we should also not forget about our physics, and the computer science people should not forget about physics and domain knowledge. And this is also, I think, one of the areas, if you would ask me what is an interesting area to look at, that's one of the domains. Now, would I recommend PhD students to look at that? There's a lot of activity there. So if I would start looking in that field, try to look for something which is a little bit off mainstream. So maybe that's for the moment all what I would say.
Yeah. Okay. Hong, you are the real foot soldier in the field. Unlike myself, who's a sort of like a wheelchair quarterback. So we want to hear from you.
Thank you. So that's a very good question. And yeah, for this round of hot wave, I will see, and nobody can predict what happens. However, there's tremendous differences from the 1990s, and the capability of computation, parallel edge computing. All this provide a very good support, like the sensors I showed, the new sensors come out. And some of the information is before is not available. So from that perspective, I'm cautiously optimistic. However, for the control community, I think the build of systematic system theory and the control theory still is a good foundation. For example, the machine learning people these days just running different algorithms for, oh, how good I can beat you with the prediction errors. But many of the practical issues like closed loop and noise, and those problems in the linear system already have a very thorough study. We build a foundation. How can we address the different situations? For example, deep learning. I enjoyed reading a recent paper, Professor Liu Yang, and about the comparison of identification framework versus the deep learning. And so the prediction side, and in the linear system, we know the SVD is very well addressed the state space model identification issue. However, in a deep learning neural network, it can be much more challenging, get a clear analysis on that. And if you are, right now, people just predict, they don't care the collinear of the input. They don't care much about the data is an open loop environment or closed loop environment, because behind that, we know in the linear system is quite different. those kind of practical issues can be a very useful topic for students to start with. And that's the first part. Second part is how can we address the machine learning model, make that more explainable and more subject to the physical constraints. Otherwise, I would tell that the industry people don't accept the model. You just see how good you are, like a black box model always described as magic, and you can predict everything. However, in the reality, if you don't give an explainable input-output relationship analysis, if you don't meet their constraints and make a good physical sense to them, they are not going to accept, because they are not going to take a risk of explode their plant or something. So that's a very practical issue. I think we should pay attention. Along that way, I think a tremendous opportunity there. However, we have to be very back to the ground and step by step to do a solid study and research to address those practical issues. That's my suggestion.
Okay, to just add to your remark, Hong.
Hong, I think your side generates echoes.
Yeah.
Hong, okay. Now
yeah, Hong. To just add to your your remarks, I also noticed at the end of your talk, you said something that essentially meaning that the machine learning models are not guaranteed to satisfy physical laws. Is that correct? This is actually the first time I became aware of that.
Sorry, I didn't hear you the last part. I switched to the earphone.
Yeah. So
can you repeat?
Right at the end of your talk, you said several things which to me seem to saying that machine learning models are not guaranteed to satisfy physical laws, physical principles. Is that correct?
Well, at least the people haven't developed the mechanism can let the machine learning model to satisfy that constraints. But people are working on that.
Okay.
And right now it's a make effort on that direction. If that issue can be addressed, that will be great advance.
Yeah, okay. All right. Then, okay. So it's good for man-made systems, not for physical systems. If it doesn't even satisfy the physical laws. Okay, so I think given the time we have, we shall now move on to the questions from the audience.
Maybe,
please.
May I ask a question to Hong? Hong, you mentioned explainability, but isn't it more safety and ensuring safe operation? So would practitioners really care if you have guarantees, even if you cannot explain what is going on? That's a provocative question. In a certain sense. So explainability, predictability would mean that it does what you would expect from a physical insight or something like that. But isn't it more like that you would like a safe operation under all circumstances?
Oh yeah, a good question. Thank you. And definitely safety always a top priority for for any of the applications. So it's basically in the real refinery or chemical plant, you know, these days with highly integrated design, it's any of the if you are not meet the safety or something, this can be have serious consequences. It's definitely very important. Yeah.
Okay.
I asked that question because if you make the if you make the plans more integrated and more complex, this explainability also becomes challenging. Because if you intertwine the components, the solution a human would choose maybe is not the optimal one, but it's the most explainable one. It's the most predictable one by the human, whereas the other option might be safe and secure. That's why I was asking that question.
Yeah, I think definitely important. Yeah, you are right. I agree with that. As also, I'm very interested in your research dealing with this safety and flexibility. Thank you.
Hi. Okay, so so I shall select the questions from the chat room indiscriminately. Just from the time they were posted. So I think this is first of several questions, the short questions, but several were addressed to, I think, to Rolf. So in your presented work, did you only use MPC just for prediction? How about sliding mode control? Is it possible to use? I guess this is my interpretation, together with your learned model. We know that MPC has the ability to predict the future by past experience. And here you are using learning system for MPC. Why? Does that mean MPC future predictions not good enough? Just one more, stay on with me off. Typical machine learning AI has adaptation learning offline. Is this learning that you're talking about being done online? Okay, off, please.
Okay, I think these are actual 4 different questions, more or less.
Right.
Maybe the first one, could you use sliding mode? Certainly, you can also use other control techniques. Now, as I pointed out, I'm think this machine learning together with the optimization-based approaches is a very good fit, because it allows you to exploit predictions in a very nice way. So you're not only making the decision based on the current point, you also include maybe predictions about the dynamics. Second of all, it allows to include constraints. And third of all, and this is also very often overlooked, it allows you in a certain sense to change the model, to adapt the model, and to also adapt the cost function or the constraints, which you can use for various things like tuning, like identifying what actual optimality means, and so on. So yes, you can use other techniques, certainly, and you should always use what you are comfortable with. I believe that these optimization-based techniques, they mingle very good with certain machine learning approaches, I would say. But it's my personal viewpoint. The second question was on if we only learn references, or if the model is not good enough. So with these approaches, so as I outlined at the beginning, you can actually learn different things. You can learn disturbances or references. So disturbances and references can be the same. If you change a reference, if you make a set point change, which you didn't predict, that's a disturbance to the plan. So it might be good that you know something is coming. You can also use it for learning a model, for adapting the model to changes. You can use learning for learning the cost function, because sometimes you don't know what you actually want to optimize, because this might be guided by the human who is operating the system. And you might sometimes also want to learn the controller, because you want to speed it up and so on. So it's not limited to this thing. So there's a whole variety. You can even learn constraints. That's also an option. The last question was on normally learning is done offline. This is very often the case. So if you train a neural network, training that online, normally this takes time. Now, what you can see is, or the question there would be, what does online and real time mean? Does it mean that the model or whatever you want to learn needs to be updated in seconds? Or can it be updated on a different time scale? Can it be updated only when you need to update it? That's the first question. The answer, and the second answer also is, we and other people also work on online learning. So on real-time learning, for example, with these Gaussian processes, we do that, and we can even do that very quickly. So even in the millisecond range, you can do that. So it's not only offline, it's also online. But I want to stress, it depends on the time scale. So what is on and offline? depends if you update your model, let's say all week, maybe months. Is this offline? Is this online? So these are my answers maybe to that question. I'm not sure if they are kind of answering all of that.
What about What about if you do online learning? And this is also being asked, actually commented. What about the computation amount? And also because you also talk about learn the controllers, right? The complexity of the controllers.
So the complexity of the controllers becomes challenging if you want to, for example, include the uncertainty directly. So if you would like to include some robustness questions and you don't learn the controller, so you could also learn, an efficient solution to this problem. But if you want to include uncertainty, for example, in these Gaussian processes, you get uncertainty information. If you want to include that in the control problem, it in general becomes more challenging. So that's the one side. Then there are approaches, as I said, for the online learning, and they are developed in the moment. Not that much, to my knowledge, for the neural network side, more for GPs and similar processes where you can actually, how should I say that, where you can update the hyperparameters and the factors you learn even very quickly. Maybe you do that via an approximation. So this is happening. For the neural networks, you see that also, but it's on a little bit different time scale. But for chemical processes, as I say, the question is a millisecond, is that important? I guess no. We also do chemical and biochemical processes. If it takes 1 minute for a bioprocess, if it takes 15 minutes, who cares?
Yeah, makes sense. Yeah. Okay, thank you, Rolf. Joe, I think I'll feed you a really challenging big question here.
Okay.
And this is from audience. What is the new technology benefits that can justify Industry 4.0 with such enormous investment?
Okay. I think that's a good question for me to really touch on now. I think we need to step back about detailed techniques rather than basically try to think about in a long time scale. So we had Industry 3.0, basically automation. Okay, well, I think 3.0 has done things to automate the control systems and other things when everything is normal. All right, so under normal conditions, you can do very good control design and modeling and so on. So for 4.0, basically we're asking to have a whole life cycle automation, including those unexpected situations, including parts that has to be maintained, and you want to do predictive maintenance rather than scheduled maintenance. Therefore, you save resources, and also including very urgent situations or emergency situations, like landing an airplane when one engine has failed. Okay, so I think we need to do automation of whole life cycle things with the help of new technologies. That's, for example, more sensors, industrial Internet of Things, and also the ability to learn from real-time data and make the cloud edge computing work for us. So I think the technologies are around us. I also think we should not just think about the problems that has been defined 50 years ago. Okay, I think we should think about problems that we maybe defined 20 years ago or defined now. The definition of problems should go beyond what's defined 50 years ago, as we have technologies now. Okay, for example, I can follow up what Han mentioned 30 years ago in that round of neural networks. In the process industries, what's actually crystallized is the use of neural networks for inferential sensors. Okay, in Aspen, it's called Aspen IQ product, and Han mentioned there are like 15 100,000 applications there. Okay, so you cannot say the previous round of neural nets did not crystallize anything, but that ability of learning from data to predict quality has actually led to something now is actually part of the MPC feedback control systems. Okay, so I think these new things or this sort of new rounds of interest in neural nets or machine learning in general, okay, can help us open up the box, really define problems that we have not defined 50 years ago. I think that should be our position. And also I want to address the question of physical models, physical understanding versus data. Those things should complement each other. And my black and white fish, the black and white part really shows that they should complement. And you always have the dark side as you fly an airplane there. You cannot know everything there. However, real-time IoT things and even cloud edge computing will help us understand the dark side very quickly and timely. That's one of the V's, one of the 4 V's in big data. Okay, you need the velocity, which means you decipher data right away. Okay, as you need it. Just imagine what we have now. Okay, we're also talking about not just on airplane to do cloud edge computing. We do it with satellites. Okay, with satellites diagnosis of satellite conditions, you can do cloud edge computing. Put the edge computing on the satellite. Okay, so this is the age we have a much more modern things around us or instruments around us. Even for us to do control, we have expanded scope of controlling things. I mentioned this one engine fail, can you still do the autopilot? Okay, so if you can do it, it's already a step forward than what we have in the past. Okay.
Okay, we shall continue with the questions from the audience. And so Hong, I just toss out a tough question to Joe. I'm giving you several easy questions to balance out. So here's it's tough for me, should be easy for you. Here's the first question. For big data and AI, modeling and analysis can be quite successful if pre-processing is done well for heterogeneous sources of data. Data pre-processing skills remain as an art, and it is much domain dependent. Does Aspen have any standard pre-processing tool being developed for process industries?
Good question. Thank you, Professor Chen. Yeah, actually, this is the requirement from practice. And if you look at today's the machine learning working flow and the profile, that's the load data, pre-processed data, feature engineering, and then training, then validation, and deploy. So the workflow very similar to the practice when we do the linear modeling or identification. And the first challenge for many of the users from industry, it is how can I easily use by some tools can automatically pre-process the data, because if you look at the real data, at least a lot of shutdowns, spikes, outliers, definitely this is the real world. And definitely important for a good pre-processing. However, very application specific. For example, if you want to build a model for the dynamics, you want some big moves, looking for some big moves and the responses, because you want to build a causal input-output relationship. However, if you want to build a monitoring model, you want to see what's the normal operation range and what's the normal operation behavior. You want those kind of signatures. So that's a different application problem and have a different data pre-processing. And on the data science side, and based on my personal experience, I think machine learning AI should not only focus on the learning. Much more new areas and advances. For example, the time series search or pattern recognition. Aspen Academy, we have another professor. It's Professor Keel from UC Riverside, and he's leading in the. Just to look at time series, he can use some algorithm very quickly to search different patterns, different similarities or differences. So those techniques can serve for the data pre-processing very well. And definitely the question, the answer is sure. We need some data pre-processing can help the user. However, some general, like outliers removal, interpolation, or aggregation. Those many of the general ones, it is okay. You can build some tools, but for specific application, what information you are looking for, that can be different. So the answer will be yes. For general pre-processing, you can develop something to do that work and easily. However, more deeper or then project specific, you need a domain knowledge involved. That's the part I always emphasize. The domain knowledge plus AR work together, like Professor Chin just mentioned, complement each other. You can get the good result.
Hold on, just a side question. Just I missed the name. You mentioned someone at UC Riverside. I came from UC Riverside. So, well, who's the guy?
Professor Keel, Amen Keel.
Amen Keel in what?
In computer science.
Computer science.
I'll send you the email.
Okay, must be new after I left. Yeah, right. I already left there 10 years ago. So yeah. Okay, sorry. Next question is also to Hong. How do you envisage APC initial assessments and collaboration between DS and the APC teams? What is the perfect team ensemble to leverage knowledge between AI and the APC?
Sorry.
Angela?
I hear baby crying.
I heard some.
Yeah. So
the first part of the question, can you repeat it? I don't want to misunderstood.
Okay, how do you envisage? What's your take on APC initial assessments and the collaboration between DS and the APC teams? Question number one. Number two, what is the perfect team ensemble to leverage knowledge between AI and the APC?
Oh, okay. Yeah, for the first one, it is a good question. And yeah, Aspen Tech also hired a number of data scientists. And so again, typically we build up teams to work together. So data science, they have a very good understanding on the data science side about machine learning, pros, cons for each of the algorithm, and to contribute to that, we know this algorithm is strong to address different aspects of the problem. But for the control person, you need to have a clear definition of what problem you want to address. That's very important, because if everything just try a different machine learning algorithm, you won't get the solid result on that. So the best team is work together, have a clear understanding and definition of your target problem. Then what's the challenge of this problem? Why the traditional approach cannot address well? And if that's clear, then you can looking for answers from a machine learning side, from the AI side. And many of the problems in Aspen Tech, not only control, like scheduling, planning, these very complex problems. If we have a very clear definition of the problem and know where the difficulty today is still not well addressed, then from machine learning side, either the good idea behind the different algorithm or the machine learning algorithm itself can well address, then you get the much better opportunity to solve that in a better way. That's my answer. I hope we can address that issue.
So Alf, we come back to you. Regarding the part on learning system dynamics using Gaussian process, is the learned system dynamics model time variant since the input-output data can be collected over the runtime of controller? If that's the case, what's the main challenge to guarantee stability when fusing MPC with Gaussian process?
So first of all, it can be time varying. It's the reference signal, and this might depend on, in this case, on the patient, how he kind of receives the operation. So it can be time varying, and in the long term, we also want to adapt that to that. So not offline, we really do the online learning. And the key challenge actual in that sense, that's the first part of the talk, is more like that you only want to learn something what you really can also achieve with your controls. That's a little bit irritating maybe for this example, because the breathing is given, but in a certain sense, you can also say we include systems insights in the learning. So I talked about including reachability. So this means this is a point where we say we want to get a model which actually the physics, which includes the physics, let's say it like this, and ensures that under all circumstances you can satisfy the constraints in a certain, that's a rough answer to that.
Okay.
Otherwise it becomes too technical.
Okay, good. And here's a question that both you and Joe may address. Since both of you have done quite a lot on system ID. What do you think of the use of subspace identification for multivariable systems with a focus on control systems? So this is not necessarily tied to AI machine learning, but on system ID.
Maybe Joe, you want to.
Yeah, my answer is very short. If that question is really about a subspace ID and how it can be used, or whether it can be used with the MPC, and I think Aspen is using that. Aspen is doing that in their products for over 10 years. So the answer is yes.
Okay. Yeah. Good. Latent process. Here's a question addressed to Jill specifically. I think DICCA, D-I-C-C-A,
Right,
is actually extracting a series of latent auto-regressive processes. If you want to improve the predictive performance, which means reducing the conditional variance given previous latent states, you need to guarantee the AR processes extracted by DICCA are stationary, so are the latent AR processes extracted by DICCA stationary. Very technical. Yeah.
Mm-hmm. Yeah, that's a good question. Actually, what's extracted by the DICCA or DICCA doesn't have to be stationary. It can have integrators, all right? Therefore, it can be ARI, okay, if you will, ARIMA, part of ARIMA. So you can do AR or ARI, but if you add MA, like ARIMA, it'll be more complete. But I think in a lot of the time series analysis practice, people are happy with AR or ARI, okay? If you want to expand that into more fancy algorithms, I think it's definitely possible to be more truthful to the signals, I would say. Yeah.
Okay, so I think we are over the time limit, but I really like this question. So this is the last question. address from the audience to all three panelists. The question reads, the success of AI machine learning in the tech industry has put a lot of pressure on people like us in the process industry to repeat that success. What's your take on the scale of success we might be able to have in the process industry, given that we are dealing with very different systems and a very different data compared to the tech industry? And there's already been decades of modeling, optimization, and control R&D operational in the process industry. So we are not starting from nothing. I think this applies to a lot of us people, not only just in the the process industry. So Joe, you may want to start.
Yeah.
Are we going to just throw away so many things that we have learned? Yeah.
Very, very good question. I like the beginning part as well, which means the success with Google and Amazon really put pressures on the chemical manufacturers and other industries. Okay. However, I think there is always the need for existing industries to adopt or adapt new things in order to survive the competition. These industries, even though they've been running for decades, they will have to evolve over time. For example, if you look at the electricity power grid, now if you just do things without thinking about renewables, you would not be able to survive. Okay, so with the renewables, the old way of doing things is going to be obsolete and it has to be replaced with smart grids. Okay, so that's an analogy I use. I will also add that for anything that happens in industry, most of the time it happens slowly. Okay, I see two things. One is people trying to rush to get on the bandwagon and to try quick things without much study and get burned quickly. Okay. I think this happened to common filter 50 years ago. Okay, but it doesn't mean common filter is not working. Okay, so that's one easy mistake to make. People just want to, without sufficient study, they just want to, okay, not translate, but just copy things to their domain. I think that's not going to work. Okay, I think we should really respect that in our industry things evolve slowly. Okay, and it's not like I would say the phone industry has evolved fairly fast from generation to generations. So we have to respect our time constant and be patient. In this domain, you see very good companies that later on they get sort of into problems. Okay, even GE now is getting into financial issues and problems. But if it's revives, okay, it'll become another leader in a different way. I think we have to look at how this technology evolution will force us to adapt. Okay, I think we need to really keep in mind that the industry will slowly evolve, but if you don't evolve fast enough, you might be forgotten. Yeah, that's my address.
Yeah.
Thank you. That's good questions. I agree with Joe. And if you look at the state-space theory, control theory built in 1990s, it's so successful in the satellites and rocket control. But back to then, the common filter becoming so hot and popular, people want to apply to the process. Even today, like I showed the example, the larger scale of model predictive control, we still have a difficulty to adapt to those kind of state-space model because you're dealing with so many input outputs. If one pair of input output model changes, if you use state-space model, you mess up the whole model. So that's a very practical issue. And so I mean, not just means that can be negative or to look at the opportunities. My take is in the process industry, not only control, not only model predictive control, the whole business have kind of multi-layers. Above the control, we have dynamic optimization, and the original optimization, just one unit, one process. Right now, it's a whole supply chain, whole production line, from crude oil in to the plastic out. So then you can have getting much larger optimization, scheduling, planning, and some of the detail of the like batch process, pharmaceutical process. There are many practical areas still have tremendous opportunities to apply AI differently. Don't just focus control MPC is the only one. That's my take. So from that point of view, tremendous opportunity, like many of them can be formulated as optimization. And some of the optimization can be well addressed by the machine learning. Either use the machine learning algorithm directly or use some good idea behind the machine learning optimization. So I think if open-minded to look at, just like you said, maybe have a different definition of problem or look at the different aspect of the reality, then you have a tremendous opportunity to gain the success.
Off, you are the youngest among all of us, so you represent the future of our society. I leave the last concluding remark to you.
I'm not sure if this is up to me, but maybe, so I agree with what Joe and Hong said, and I would also see it differently. I would say use the opportunities where you can use it. So don't blindly use it, the technologies from machine learning everywhere. Try to identify where you can use it in a useful way and exploit that. Don't see it as an opponent, see it as a possibility. That's the first comment. And then maybe also commenting on the tech side, if one carefully looks at that, it's exactly like that. So machine learning is widely used for image analysis, data analysis, predicting customer demand and things like that. Now, if you look a little bit more careful into control-related things, this is a question I always ask my PhD students, what are really the success stories of machine learning? There are some at Aspen, for example, but if I look at that, if you look in detail, autonomous driving, people say this is machine learning. Yes, they do machine learning for perception. Do they do machine learning for making the decision? I would be a little bit more skeptical about that. So on that side, I would not see it as a competition. Especially the process industry is a little bit slower. It takes a little bit more time. It has more money which is invested, but there could be new players on the ballpark who solve specific problems. They will not be able to solve all problems. So I would not be afraid about that. But maybe last comment, yes, there is a lot of people who put a lot of pressure, and these are the people who don't know the technology. They just say AI is perfect. Can't you solve my problem with AI? And they have no clue what they are talking about. So maybe that's the dangerous part.
I really like your comment, the last one. Makes me an older man, confident again. Yeah. So with that, we are ready to conclude this session. I really enjoyed this whole thing from the very beginning to the end. It has been wonderful, exciting evening for me. And thank you, Hong. Thank you, Joe. Thank you, Off, and for the excellent talks and for the brainstorming. Everything just comes together perfectly. And Mark and Sandy, I would also like to thank you for making all the arrangements to make this possible. And above all, I would like to thank our audience. Yeah, no matter where you are right now, you may be even later than we are in Hong Kong. So, so I would like to bid you good evening, good morning, and good afternoon. Everyone, please stay safe, and let's look forward to Module 2 and Module 3, and keep a mind on the schedule. So we shall meet again. Yeah. Best wishes to everyone. Good night.